And let's start the lesson. Well, first, it's an introduction to the world or the global issues in terms of energy, in terms of energy consumption, in terms of fuels, or in terms of energy sources that we have. What we are going to do in this course, we are going to analyze details, thermal bridges and moisture, and then we will look at solar design features and building energy modeling. So we're not going to do that today. We're going to explain with the analysis of details. And we will explain what thermal bridges are and how moisture inside the walls or inside the roofs can affect the performance of the building. But first, we have this, okay? So we know that the world population is growing. We are here around in 2023, and the projections by 2030 is that the world population is going to increase, but the energy consumption is increasing even. So the slope of this line is steeper because we will have more energy consumption, or the growth of the energy consumption surpasses the growth of the world population. This is because our style of life, we demand more energy than 50 or 100 years ago. Now we have a lot of devices, and all those devices run on electricity, and we need more electricity than we needed a few years ago. So we need to increase the electricity generation. So unless this changes, unless the world population goes down, or unless the energy consumption goes down, what we need is to generate electricity. And what are the sources that we have to generate electricity or energy in general? We have oil, gas, and coal. Those are fossil fuels. We have nuclear, and we have renewable energies. Okay, so this is what we have. This is there are other sources like hydrogen, but hydrogen, it's something that has to be generated with either nuclear energy or renewable energy or burning fuels. Okay, so far at this point in human history, we are here between 2020 and 2025. These are the ways that we have to generate energy. And look at the distribution. So fossil fuels are the most important source of energy generation. So it's like 3/4 of the energy that we generate in the world comes from fossil fuels. We have to burn oil, gas, or coal. Coal is mainstream because in, let's say in developed countries, gas is mainstream now. But in non-developed countries, coal is the main source for energy. Then we have nuclear. Nuclear is steady, it's not growing. Okay, so we generate almost the same amount of electricity by nuclear plants as we did in 2006 or in 2000, so it's not growing. And renewables are growing little by little, but we are far from being in a totally renewable world. So that's a fact, and we have to be aware of that. And the projections by 2030, which is the near future, in 7 years, are that we will continue this. Probably the renewables will grow a little, but most of the energy will be generated by fossil fuels. If we look at the renewable energies, what are renewable energies? Well, we have these 4 main sources for renewable energies. We have hydropower, wind, geothermal, and solar and others. Well, let's say solar. Hydropower, we have dams, and we can generate electricity by accumulating water, and then we release that water, and that waterfall with turbines generates electricity. So this is renewable, but hydropower has an impact. It's renewable energy, but it doesn't mean that it doesn't have an impact. If we look at, for example, the okay, so this is a way to generate renewable energy, but it has an impact in the landscape. We need a dam, and then we need to accumulate water on the other side, and then we release the water, and here we have the plant that actually generates electricity. Okay, so it's considered renewable, but again, building this kind of dams has a huge impact on the landscape. Okay, so that's the most important renewable source in terms of electricity, especially electricity generation. Then we have wind. We all know what wind all these wind generators. We have this, again, it has an impact in the landscape. Okay, so it's renewable energy, but it impacts the landscape, and it impacts the life, especially birds around those kind of installations. And the problem with this is that we need a huge amount of area to generate electricity. So it's not something that we can, so it impacts a lot of area. Okay, so by installing one of them, it doesn't make any sense. We have to install lots of them to generate enough electricity. So that's the wind. Then we have the geothermal. What is the geothermal energy? Well, geothermal means, so there are some places in the world in which we have a heat source which is shallow. Shallow means that we have hundreds of feet. Okay, so it's not just right here, but at 500, 600 feet, we can have enough heat, and then we can extract that heat and then can move turbines, and then we can generate electricity again. Okay, so that's the geothermal, and it happens, well, there are specific points on Earth in which we have this heat source close enough to the Earth's surface. So that's the geothermal energy. Does it impact? Well, it doesn't impact a lot because basically we have to dig something, okay, and we dig until we found the heat source, and then that heat can generate that steam, and that steam moves turbines, and then it generates electricity. So those are geothermal plants, okay. But again, we can do this at specific points in which this heat source is shallow enough. Okay, if it's too deep, we can't do that. But this is what we consider the geothermal energy. There is another geothermal energy that has to do with heat pumps, but here we are talking about hundreds or thousands of feet to get to this heat source. What we consider a shallow geothermal energy, it's something that we can connect to heat pumps in buildings, and we are talking about maximum 100 feet or something like that. Okay, it can be 50 to 100 feet, but if we go deeper, like 500 or 1,000 feet, something like that, we have another kind of geothermal energy. Okay, we will speak about both. This is something that we can apply to our buildings. This is something that we can't. So we need to be in a place in which the heat is close enough to the Earth's surface. But this kind of geothermal energy, this is something that we can apply to our buildings. And finally, we have solar. Okay, so you see the geothermal energy, it's well, it's very little compared to other renewable energies, because there are specific points on Earth in which we can make the most of that heat that we have there. And then finally, we have the solar. So when it comes to solar energy, there are different ways. So we have photovoltaic PV arrays like this. Okay, so those are PV panels. We can place those PV panels in the middle of nowhere, or we can place those PV panels on the roofs. Anyway, we turn solar heat or solar radiation into electricity with these PV panels. There are other plants which are plants like this. Those are not PV panels. Those are mirrors, and those mirrors concentrate, as you can see, they are all focusing on that point, on this tower, and then the solar radiation is reflected towards the top of this tower, and the temperature is so hot here that it can turn water into steam, and that steam can move turbines. Okay, so this is solar energy, but those plants are something different. It has a huge impact because we need all this area of, those are not panels, those are mirrors, and by reflecting the solar radiation, they focus all the solar radiation on the same point. So that's why we have like circles here, because all this solar radiation is reflected to this point. And at this point, we have such a high temperature that it can move turbines as well. Okay, so we have different solar plants, but those are not the same panels as we have here. Well, those are solar panels, and those panels turn heat or solar radiation into electricity. Those are not panels, those are mirrors that concentrate all the reflected light at this point. And at this point, we create high temperatures. And with this high temperature, we can turn water into steam. And with that steam, we can move turbines. Okay, so this is solar energy. This is solar energy, but the process of energy here is completely different than here. Okay, so, but again, we have an impact, okay? When either if we work with PV panels or we work with the other panels, it impacts the landscape as well. If we don't want to impact the landscape, but we want to impact our buildings, we can do this. We can place PV panels on our roofs. And if we have enough PV panels, probably we can generate as much energy as we are consuming in that building. Okay, so there are two ways to address this solar energy. We can have plants in the middle of nowhere with thousands of PV panels, or we can have PV panels on our roofs, and then we can generate the electricity that we need in this building, if we have enough roof area and if the orientation is the right one. Okay. So basically, this is what we are going to do in this course. We can't, well, we could study these kind of plans, but this is not the scope of architects. In architecture, we work with buildings, and if we want to generate electricity in our buildings, so it has to be these ways. How can we generate renewable energy in our building or in our site? By means of solar panels or solar collectors. And do we use this kind of, no, we can't place, look at the size of those wind generators, they are huge. So we can't place this in our building. Okay, so it's something that we can't place in our buildings. It has to be in the middle of nowhere or offshore in the sea. Anyway, so we can't, or it's difficult to integrate wind generators in buildings. And when it comes to the geothermal energy, we can work with this. Okay, so we can connect buildings to these holes, and the depth of these holes is around 50 to 100 feet. And we use this to work with water-to-water heat pumps. Okay, so this is not the geothermal energy that digs until we have a heat source. This is a way to interchange heat with the soil. Okay, but we have to go deep. Yeah, we have to dig until 50 or 100 feet. So those are the two ways that we have to work with renewable energy in buildings. We can use this geothermal heating and cooling, but the shallow geothermal is not the geothermal that make the most of the heat that we have deep inside the Earth's surface. And then we have the solar panels. The solar panels on roofs. Okay, so hydropower, it's not in our realm, so we cannot. Well, we can create small hydropower plants if we have a creek or we have a small river in our site, but well, it's not in our building. So for buildings, we have the geothermal, the shallow geothermal, and we have solar energy. This is all we can do to generate renewable energy in our buildings. But most likely we will keep burning coal, gas, or oil. Burning coal, it doesn't make any sense nowadays. So most of the heating systems are made of gas or oil, or we have other fuels like kerosene or gasoline or whatever. But gas nowadays is mainstream for many reasons. First, because it has more power density. So burning gas, we can generate more electricity than burning oil or coal. And it's easier because in the cities, we have gas ducts or pipes. So we can connect our buildings to the city infrastructure with gas. And well, gas is mainstream, and especially it releases less greenhouse gases to the atmosphere than coal or oil. Okay, so gas in terms of fuels nowadays is the best thing we can do. And then for renewables, we have the geothermal or we have the solar panels or geothermal boreholes. Well, I'm going over this but it's not something that I'm making up. I abide by the Department of Energy. So the Department of Energy of the US. So here we have well, we have a lot of information, and here we have what they consider energy sources, clean energy. So let's look at energy sources. Okay, so first we have fossil fuels, coal, oil, and natural gas. This is fossil fuels. Then we have hydrogen and fuel. Well, this is still developing, this hydrogen technique. And that's great because what do we have after generating hydrogen? What we have is water. When we burn fossil fuels, we have CO2 and other greenhouse gases. But when we generate hydrogen, we just have water. Okay, and so that's probably the future. But nowadays we don't have the technology to produce clean hydrogen. Most of the hydrogen that we can produce today, it's by burning fossil fuels. So again, it doesn't make sense so far. But probably this is the This is the future. And then we have energy storage. The energy storage is one of the most important issues that we have. If we could have energy storage for electricity, that would be great. But so far we have batteries, and batteries are expensive, and they are very big if we want to store a large amount of electricity. Okay, so energy storage probably it's the challenge that we have nowadays. We have electric power. Well, we all know what electricity is. Electricity is great. We can apply electricity to everything. All devices that we use on a daily basis run on electricity, and we can use electricity to heat up or cool down buildings. So it's great. The problem is how to generate electricity. We can generate electricity with renewable energies or by burning fossil fuels. And the problem with the electric energy now is that nowadays we don't have a good energy storage for electricity. And finally, we have clean energy. So what do they consider clean energy? So clean energy, it's solar, wind, water, geothermal, bioenergy, and nuclear, and hydrogen. Okay, so this is what the Department of Energy considers green energy. We can, yeah, it's very easy to think that, okay, solar, wind, water, those are renewable energies and they are clean because they don't generate any greenhouse gas. But what about the geothermal? Well, it's clean energy. We don't have to do anything, just we have to dig a hole until we get this heat source. So it's clean. We don't release CO2 to the atmosphere. By bioenergy, I have my doubts about this, because bioenergy, it's about burning. It's not a fossil fuel. It's by burning plants or by burning biomass. So biomass, it's a fancy name for wood. Okay, so mankind has been burning wood since the beginning of civilization to generate heat or energy. And now this is biomass because it's not just wood. We can burn something else that was alive once. Okay, but the problem is that by burning this, we generate CO2. Okay, so I don't know, it's considered as a clean energy, but it's not as clean as others. And finally, we have nuclear. Nuclear is clean. It doesn't generate all these elements. Those are not chimneys releasing smoke. Those are cooling towers releasing water steam. Okay, so it has an impact, but it has less impact in terms of area than, for example, solar plants. Okay, we might need like thousands of acres of solar panels to generate the same amount of energy that a nuclear plant can generate. So it's clean. It's it doesn't generate any greenhouse gas. It generates electricity. It's very efficient, very effective. The problem that's it's safety. Is that a problem? Well, I don't know, but there have been a couple of accidents in nuclear plants, and usually people are scared of nuclear plants. And then we have this hydrogen again. And hydrogen itself, it's clean. The problem is the way we have to generate hydrogen. If we generate hydrogen by burning fuel, fossil fuels, then it's far from being green. If we can generate hydrogen out of renewable energies or nuclear energy, then it becomes a clean energy. Okay, so this is when there's a lot of controversy about what should be what the future energy source should be. The world moves towards the renewable energies, but renewable energies, if we don't have sun, we don't generate electricity. If we don't have enough wind, we don't generate electricity. If there's a drought and we don't have water, we can't use this. So we can't rely 100% of renewable energies so far with the technology that we have nowadays. So fossil fuels are still important. Nuclear would be great, but the trend is that it's only like 10 to 20% of the energy that we generate in the world by nuclear plants. So that's it. Anyway, we need to know that, and we need to know where we are. And this is something interesting. We have net electricity generation. There's a difference between OECD countries and non-OECD countries. What is this OECD? Okay, so this is a club of countries, and here we have the countries that belong to this club. Those are what we consider developed countries. Other countries are developing countries. So in these countries, there's well, there are certain conditions that make them belong to this club. Okay, so how many of them we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, there are like around 40 to 50 countries that belong to this club. Well, usually on these countries, until the beginning of this century, those countries generated most of the energy of the world. But after 2010, that changed. And by 2015, the countries that don't belong to this club, they generate more energy or more electricity than the developed countries. Why is that? Well, because a developing country needs to generate a lot of electricity to become a developed country. And we can find in this club, we can find India or China. And nowadays, India and China are consuming and generating a lot of energy in the world. Okay, so those countries are growing and are growing because the OECD countries, they have steady energy generation and consumption, but the energy generation and consumption of other countries is growing a lot. So that means that we need more energy. We, as the world, needs more energy. And as these countries are becoming developed countries, they will need a lot of energy to achieve the accomplishments that OECD countries have done over the last decades. Okay, again, is it something that we can control as architects? No, it's but we need to be aware of that. We need more energy now than we needed 20 years ago, and in 2030, in 10 years, we will need more energy than we need now. Okay, so we have to find more energy sources because the trend is that the energy consumption is growing in the world. What about renewable energies? What about, oh, and there's another thing here. Look at the fossil fuels, oil, gas, and coal, especially coal. That's a concern because the coal consumption, it's growing And coal, in terms of greenhouse emissions, is probably the worst fuel that we can use. Okay, gas is growing. Oil, I think it's decreasing, the oil consumption to generate electricity, but the coal is growing. So that's the nuclear is almost steady, and renewable energies are growing, but at very slow pace. Okay, so this is what happens worldwide. In terms of renewable energy, which country is the country that produces more energy out of PV panels, out of solar energy? It's China. Okay, probably China is also the country that consumes more coal, but well, it's such a huge country that probably it's the first in all the statistics. Then we have Japan and the USA. So those are the countries that produce more energy out of solar energy. Okay, and then we have all these, the rest of the countries, probably most of them in Europe or in India or in South America. Okay, and then the rest of the world. But these three countries, probably they are the three countries that produce more solar energy, but probably they are the three countries that burn more fuel as well. When it comes to solar energy, there are different strategies. And here we have different examples in Europe. I have these statistics from Europe, but the example of Romania or Spain is completely different than the Netherlands or Portugal. And this is politics. This is about strategic decisions of how the country is addressing the energy issue. We're talking about the solar energy. In these countries, in these two countries, what is mainstream is large scale. Okay, so that means large scale solar plants is this. Okay, so we have like this huge area covered by solar panels. So some countries are doing this, a large scale, but other countries are making the most of the roofs with residential. Okay, so they are placing PV panels on roofs. It can be either commercial buildings or residential buildings. So these two countries, they don't have large scale installations. Those countries, they don't have PV panels on roofs. Why is that? Well, I know Spain, I know the Netherlands. The Netherlands, it's a tiny country in terms of area, and it has a lot of buildings on it. So it makes sense that most of the PV panels are on the roofs. Spain, it's a big country, and there's a lot of open space. So it's the perfect place for this kind of PV. They call it PV farms. It's farming. Okay. Anyway, so that depends on the country, but there are two strategies when it comes to the solar energy: either a large scale in the middle of nowhere, or placing PV panels on the roof of the buildings. What we can do is this. Again, in architecture, we can't do this. We can integrate PV panels on our buildings with that strategy. But again, it depends on the country, it depends on the area of the world, and there are strategic decisions that are made by governments or whatever. And when it comes to PV panels or photovoltaic panels, we have the crystalline, the thin film, and new technologies. We will talk about this, but I don't know. Crystalline, it's mainstream, but other technologies like the thin film and other new technologies are becoming more and more important. Why is that? Well, because probably they are cheaper to manufacture, but at the same time, they are less efficient. We'll talk about this when we are talking about PV panels. And Well, the title of this course is Building Science 2 and Solar Energy. So we are going to focus on solar energy. But it's something that doesn't depend only on the architect. It depends on different types. Okay, so when we are thinking of solar energy for our buildings, these are the questions that we have to ask ourselves. First, what is the site? What's the area and the orientation of our roof? Do we have shades? Okay, so we have to analyze our site. Geographic location, how much sunshine per year? So we need to know that. Is it worth placing PV panels? If it's always cloudy, probably it's not worth it, but we have to analyze it. And this is something that we can't control. It's about tax deductions, certificates, building regulations. Well, if there are advantages for integrating solar panels in our buildings and our clients can benefit from that, we as professionals should be aware of all this. The problem is that this jurisdiction or these regulations change, and something that can be good today, in 5 years, if the law changes, it can be completely different. But anyway, we should be aware of that. Motivation, I think that's important. What's the primary motivation for going solar? Return of investment. Okay, I go solar because there's a good opportunity. Now there are subsidies or tax deductions. And if I place PV panels on my roof, it will be, I will have a good return of investment. Okay, that's a powerful motivation. Increase their renewable portfolio. Well, nowadays, some companies, they can attract clients by betting on renewable energies. So that's another motivation. Well, it's money. Capture market opportunity. Again, we can attract clients if we show our clients that we are renewable and we are committed to sustainability and all that stuff. Okay. Reduce the fuel price risk. Well, if fuel prices keep increasing, being solar, it's a good way to avoid those risks of energy prices. Okay, but again, all these motivations are triggered by money. And then we can save the planet, we can reduce carbon emission, and we can make our community to feel good, okay, by reducing carbon or CO2 emissions and by contributing to a sustainable future. Okay, so those are the motivations. Most of the motivations, we don't have to be naive, it's about the money. Okay. But we can find clients that really want to reduce the CO2 emissions and they want to go solar because they want a better future. Okay, but we need to know if after this motivation, probably the second question will be about money and will be about the return of investment and how much money does it cost and how much energy do I generate per year. So that's it. Then after analyzing all this, if we go for it, what sources of finance are available? Again, we need to know that because nowadays we can find a lot of opportunities to improve the financing of these solar projects. And finally, we have to apply this. What do we want? Do we want electricity, or do we want for appliances, or do we want heating and cooling? Do we connect our system to the grid, or it's just a we don't want to connect our system. We want a standalone system. Okay, so as you can see, it's not a straightforward decision. Okay, let's go solar. If the site and the geographic location are not appropriate, it doesn't make sense. If we find a state or a country in which or that doesn't offer any advantages to people installing PV panels, most likely we won't do it. Then we need a client that is motivated. It can be for money or it can be motivation for saving the planet, but we need a motivated client. And then once, after analyzing all these, we decide, okay, let's go for solar. Then we need to develop the project and we need to take care of the financing because, okay, but what we can do, we can analyze and then we can apply. This is what we can do as architects, and this is what we'll be doing in this course. Okay, so we will analyze the site characteristics and the geographic location, and we will assume that the jurisdiction is good and the motivation of our clients is good, and that we will have a good financing, and then we will apply, we will create a project with solar panels. Okay, but in the real world, we have to take all this into account before doing this, before actually designing the project. So what are the reasons for not buying solar? High financing cost upfront, perceived to be too intermittent. That's the problem, and it's not just perception. It's true. If there is no sun, we don't produce any electricity out of PV panels. And finally, we don't have a brand name. I would like to ask you if you know a fancy manufacturer of PV panels. I know that Tesla manufactured batteries. Okay, this Powerwall. I remember that they tried to create a brand that people could recognize related to PV panels, and they manufactured batteries. But as far as I know, it's not mainstream. Okay. Why? Well, probably because it's too expensive, or well, there are many reasons. But anyway, other than Tesla, I can't name any brand that it's. We know brands for everything. We know brands for soft drinks, for clothes, or fashion, or whatever. But for PV panels, there is no brand name. Okay, so all these things make those are barriers to use solar electricity or solar panels massively. Again, can we do anything about this? As architects, we have to look for financing, and yes, it's too intermittent, so we have to either place batteries or to connect our building to the grid. If we connect the building to the grid, and if we don't generate enough electricity, we can get electricity from the grid. Okay, so that's it. The payback period or internal rate of return. Okay, so this is a formula, and well, we can try to calculate this. So that means that what is the time in which I recover the investment? Well, so we have the initial cost, we need the cash flow, the cash inflow. It's the money that we save because we have installed renewable energies during the period T. So at the end, we should calculate T, which is the amount of time, it can be years, in which we recover the investment. It's a complicated formula, but we will explain this in the future. Okay, so this is an introduction to solar design, and those are the reasons that might affect the solar design. Okay, those are global issues, and then here when we are dealing with a specific project, we have to answer all these questions, especially this one. This is what every single particular client will ask you. And what is my payback period, or the internal rate of return, or the net present value? Okay, so those are concepts, and we need an answer, because if this time is more than 10 years, nobody will go for it. So we have to figure out how to do this. So we can do this by reducing the price of the PV panels, or by increasing the finance opportunities. But if this number is more than 10 years, nobody will go for this kind of solar. Anyway, today we want to focus on that, and for the next few classes, today and on Wednesday and next week, we will be analyzing details in terms of thermal breaches and moisture. As I told you, moisture inside the buildings, or not inside the building, inside the wall or the roof itself, is one of the worst things that can happen. Something terrible, because water will show up here in the middle of the wall. We won't notice that this water is getting liquid, and it will affect the structure, it will affect the thermal insulation, and it can ruin the whole wall or the roof or whatever. We have tools to analyze what happens in a real building. If we have to refurbish a building, the first thing we should do is to work with thermal cameras like this, and then we can detect where the issue is. So here the issue is that we don't have thermal insulation on these rafters. We have the thermal insulation between rafters, or between studs. Those are studs because it looks like a wall. But we don't have thermal insulation here, so that's an issue. Looking at this, what we should do is to cover either indoors or outdoors the studs with thermal insulation. So we can use this tool, the thermal camera, or the infrared imaging, to analyze existing buildings, to understand what's going on before at the project stage. We can use software, and we will be using Therm. Okay, so on Wednesday, I'll start explaining how this Therm works. But before that, today I'm going to show you another tool. Okay, so we will be working with different tools to analyze what's going on here. Why are thermal breaches? Well, first, what is a thermal breach? A thermal breach. Well, basically a thermal breach is a place or a spot in a building in which the heat follows the path of least resistance. And what is that? If we interrupt the thermal insulation, then we have a thermal breach. Okay. So where do we have a thermal break? If we have thermal insulation, if this light green is thermal insulation and this is thermal insulation, this thermal insulation is interrupted here. This is outdoors, this is indoors. So there's a thermal break, and the heat tends to go in this direction. Okay, so that's the thermal breach. If we have a wall, usually we don't have thermal breaches. But if we have a floor-to-wall transition or a wall-to-roof transition, then it's very easy that we can have thermal breaches because at some point we interrupt the thermal insulation. This is a thermal breach. Okay. So why are they problems? Because of the heat loss is the weakest point in the thermal envelope, and we lose heat. We interrupt thermal insulation, we have more heat losses. Okay, so this is the first thing, the first reason that we should avoid thermal breaches. Unwanted heat. The heat loss happens in winter. Unwanted heat happens in summer. If the outdoor temperature is warmer than the indoor temperature, then it's the other way around. Through the thermal breach, we had unwanted heat in our building. Cold internal surfaces. Okay, so that's something that we can't see, but we can feel. This is a thermal breach, by the way. We interrupt thermal insulation here, and here we have a thermal breach. If we touch this part of the building, or this part of the wall, it's colder than that part of the wall, because we have a thermal breach. We don't have thermal insulation, so we can have cold internal surfaces. It's something that it doesn't affect. Well, we can't see that, but if we are close to a thermal breach, we can feel that the temperature there is colder than it should be. Okay, so it's in terms of comfort, it's not good having cold internal surfaces in a wall. And then risks to comfort and health. Those cold spots. Okay, so those cold internal surface, it's not just that we feel uncomfortable because of it's not warm enough. If condensation occurs, or even worse, mold, then the indoor quality will suffer, and it can bring diseases, and people can have difficulty to breathe. So we can have condensation, or we can have mold. What is mold? This is it. Okay. So when we have moisture and the temperature is cold enough, we have these kind of things inside our house. And well, first, it's disgusting. We don't like to see that. And second, some of these mold can be dangerous for health. Okay. So be careful with that. And that happens usually when we have thermal breaches. And when it happens, it means that inside is even worse. Okay, when we see this in this layer, that means that inside the wall it's completely spoiled, and we have to fixing this. It's very difficult, especially because when we are aware of that, all the damage is there, and probably we will have to replace this wall, because there is no solution to solve this. Where does it happen? It always happens in corners. It happens in the basement, especially when we have a basement and we have soil, and so at the top of the basement we can always have this kind of mold. Okay, so again, it's something that people don't like, and at some point it can be dangerous depending on the living creatures that we have here. It can be a threat to people's health. So that's it. This is all what thermal breach can bring. Everything is negative. We can have heat losses, so we will end up paying more money because of the heating system. We can have unwanted heat, so we will end up paying more money for our cooling system. This affects comfort. It's not comfortable being close to a cold internal surface. And finally, if condensation and mold happens, that can bring a risk to our health. Okay, so that's the explanation. This first happens inside or within this wall. We have water vapor, so people sweat, the water vapor tends to escape. And if we don't do anything, as it gets colder and as we get closer to the outdoor air, the temperature gets colder. At some point, it condensates, and this water starts here. The mold starts within the wall, and then little by little it goes towards inside, and it shows up here. But when we can see the effects of this inside, that means that the rest of the envelope, the rest of the wall, it's already damaged. So what can we do? Or how can we apply building science to prevent this from happening? Well, the first thing we need to know, and this is what we are going to do today, is to analyze the temperature within the wall. So this is the indoor temperature. It's comfort temperature, around 70 Fahrenheit or whatever. This is the outdoor temperature, can be 20 Fahrenheit if it's winter. And then there will be at these interfaces that, well, we have 3 different materials here. So we have to be able to know the temperature at these points. And by knowing the temperature at these points, we can understand if there's a risk for condensation. So this is what we are going to do today. We have a wall made of different layers. And we have the indoor temperature, we have the outdoor temperature. So we are going to try to define the temperature within the wall. How can we do that? The formula is this. So we are going to apply this formula. But to apply this formula, we need to remember some of the concepts that I'm sure you learned in 260. The first concept is the thermal resistance. What is the thermal resistance? It's a quantification of how difficult it is for heat to be conducted. Okay, so that's the thermal resistance. Go to Wikipedia. Okay, so that's the definition of thermal resistance, is a quantification, measurement of how difficult it is for heat to be conducted. So if an element, if a construction material has a high thermal resistance, that means that it's a thermal insulation, because it's very difficult for heat to go through that material. Okay. So what do we need? We need elements with high thermal resistance. And what is that? It's a thermal insulation. So that's why thermal insulation is very important. We need to increase as much as possible the thermal resistance of the building. But if we have different layers, each material has a different thermal resistance. Okay, and the total thermal resistance of the wall, we have to add up all the thermal resistances that we have in different materials. What is the formula for the thermal resistance? Is the width of the material, this width, divided by the thermal conductivity. And the thermal conductivity is a property of the material itself. The brick has a thermal conductivity. The thermal insulation has a different thermal conductivity. And the gypsum and the board or the wood or whatever, each material has a different thermal conductivity. And then the width, it's something that we control. It can be 2 inches or 5 inches or 10 inches. It's something that depends on us, on architects. We can control the width of this material. If you remember, there are 2 layers one layer inside and one layer outside. And we have this H coefficient. This is the convective or heat transfer coefficient, which is this H. Okay, so that depends on the air convective heat transfer coefficient. That depends on the air that we have inside and the air that we have outside. Okay, so this air is the first barrier to the heat that tries to escape. If this is inside and this is outside, the heat flow, this Q, tends to go in this direction. So each material is a barrier for this movement. So the first barrier, the first thermal resistance is offered by the air that we have here close to this surface, and the air that it's close to the external surface. Okay, so this is this coefficient, this heat transfer coefficient due to convection. Remember that when we have a gas, we have convection. So this is air, we have convection. When we have solid elements, we have conduction. Okay, so this is the heat flow through solids. It depends on the thickness or the width of the material, and it depends on the thermal conductivity of this material. Okay, so this is not new. I'm explaining it fast because you are supposed to know this. If you have any questions about this, get back to me or let me know that you have some questions, because I take for granted that you remember this, that you have already done this in 260. Okay, so you have calculated the thermal resistance of different walls that are made of different materials. Remember that first we have the thermal resistance because of this air layer inside, then we have material 1, material 2. Well, in this case, we have the same material here and there. And then we have the thermal resistance due to the air layer that we have outdoors. Then we add everything up, and we have the total thermal resistance. Okay, so this is the formula. Let's analyze this formula. The R total is the total thermal resistance that we have here. We add up all these thermal resistances, and this is the R total. The RS12, it's the thermal resistance of one layer between surface 1 and surface 2. If this is surface 1 and this is surface 2, so it's the thermal resistance of this material. If this is surface 2 and this is surface 3, so that would be the thermal resistance of this material. And then the temperature, this is the temperature of surface 1 minus the temperature of surface 2. If this is surface 1 and this is surface 2, so if we want to calculate the difference between these two temperatures, T1 and T2, so this is the thermal resistance of that layer divided by the total thermal resistance, and then multiplied by indoor temperature minus outdoor temperature. So this is the indoor temperature, and that's the outdoor temperature. Okay, so that is the formula that we are going to use to calculate the temperatures. So we know indoor and we know outdoor temperatures, and then we need to calculate this T1, 2, 3, or whatever. Well, this is T1, this is T1, 2, this is 2, 2, 3, and this is 3. Anyway, we have to calculate the temperature that we have in this interface that separates material 1 from material 2. Okay, so if we are analyzing thermal breaches, or we are analyzing the risk of condensations, or we are analyzing the risk of this interstitial condensation, and then the risk of this mold. The first thing we need to know is temperatures here. Okay, so let's do it. First, we have this table, and these are the coefficients that we are going to use. This HI, it's the convective coefficient indoors. This is the convective coefficient outdoors. Here we have international units and imperial units. If we are working with imperial units, you have to look at these values. And what's that? Well, when we have a vertical element, this is a wall. When we have a horizontal element in which the heat flow goes up, this is a roof. And if we have a horizontal element in which the heat flow goes down, this is a floor. Okay, so if we are analyzing roofs, we have to use these two values, 1.6 inside, 2.93 outside. So on this slide, we have the first example. Okay. So here we have three materials. We have plywood. The width is 1 inch. This yellow material, plywood. The second material is the thermal insulation. It's fiberboard. Thermal insulation, 5 inches. And finally, we have brick. And we have 4 inches here, 4 inches of brick. This is indoors. Indoor temperature is 70. And this is outdoors. Outdoor temperature is 20 Fahrenheit. Okay. What are the coefficients if we are in this wall? The coefficients, indoor coefficient is 1.6 and outdoor coefficient is 2.93. Okay, so the thermal resistance is 1 divided by 1.6. This is the thermal resistance of this indoor air layer or interior air layer. Okay, so it's always 1 divided by the coefficient. If the coefficient is 1.6, this is 1 divided 1.6, 0.625. So this thermal resistance, this is 0.625. Then the second material is the plywood. So the plywood is 1 inch. And the thermal conductivity of plywood is 0.8. I'll explain where I take this from. And this value, 1.25, is 1 inch divided by 0.8. So this is 1.25. Okay, so that's the thermal resistance. The second thermal resistance is 5, which is the width or the thickness of the thermal insulation, divided by the thermal conductivity. So if we divide 5 divided by 0.28, this is 17.8, and here it's 18.05. Okay. Should be 17.8. It's 5 divided by 0.28. Okay, so it should be 17.05. So there's a small mistake here. Probably I rounded up from 17 to 18. And finally, we have the brick. So if the width is 4 and the thermal conductivity is 5, 4 divided by 5, this is 0.8. So that's correct. And finally, we have the the exterior air. So what is the coefficient? Is 2.93. So 1 divided by 2.93, this is 0.34, which is this one, 0.34. Okay, so this is 1 divided by the first coefficient. The first coefficient, the interior coefficient, is 1.6. So 1 divided by 1.6 is 0.625. Then we have the width, 1 inch, divided by the thermal conductivity. The width of the second layer divided by the thermal conductivity, the width of the third layer divided by the thermal conductivity, and finally 1 divided by the exterior coefficient. Okay, then this is the thermal resistance of each layer: 0.625, 1.25, 18, 0.8, and 0.34. I add everything up, and this is the total thermal resistance, 21.07. This is the total thermal resistance. Okay, so here I have the thermal resistance of each layer, and here I have the total thermal resistance. Indoor temperature is 70, outdoor temperature is 20. So what's next? Look at this. The first temperature is 70. The last temperature is 20. So I have to calculate T1, 2, 3, and 4. The first temperature would be 70. The last temperature would be 20. And this is the formula. What is temperature at point 1? Is the previous temperature, which is 70, minus the thermal resistance of this layer, 0.65, divided by the total thermal resistance, 21.07, multiplied by indoor minus outdoor temperature, 70 minus 20. So that temperature would be 68.5. This temperature 1 would be 68.5. Second temperature, T2, is the previous temperature, 68.5, this one, minus the thermal resistance of this layer, of the yellow layer, divided by the total, and multiplied by indoor minus outdoor temperature. T3 at this point is the previous temperature, 65.5, minus the thermal resistance of this layer, divided by the total thermal resistance, times 70 minus 20, indoor minus outdoor temperature. T4, previous temperature, 22.7, minus thermal resistance of this, divided by the total thermal resistance, times 70 minus 20. And finally, if we want to check that everything is correct, if I do the same here, the result should be 20. The previous temperature, 20.8, which is T4, divided by the thermal resistance of this layer, it's 0.34, divided by the total thermal resistance, and then indoor minus outdoor temperature. So this should be 20. So if at the end we start with this indoor temperature, and after doing all this, the last temperature here is outdoor temperature, that means that this is correct. Okay. So this is what we have done. First, we need the materials, we need the thermal conductivities and the widths. Where can we find thermal conductivities? Well, there are different options, and I think on Canvas, okay, on Canvas, on this first module, you have different things. you have the thermal conductivity database. If you click here, this is the engineering toolbox, a quite good online tool. And here we have thermal conductivities. We have a lot of materials, hundreds of materials. And here we have the thermal conductivity. What's the problem? As always, the problem, the main problem that we have in this scientific community is the units. Okay, so you see that the black numbers are in international units. If we want, here, if we want the imperial units, I need to click on this. Okay, so the blue values are the imperial units. Is it enough? No, it's not enough, because those units are BTU divided by feet, hour, Fahrenheit. These are the imperial units for thermal conductivity. But in this table, the units are BTU, inch, hour, feet square, Fahrenheit. So we have to convert those units. So it's a mess. So that's why I have created this Excel file that I'm going to share with you. Okay, so it's still under development. So this is not done yet. Okay. And here, this blue line is the temperature across the wall. And here in thermal conductivity, in this tab, we have the thermal conductivity of materials, air, asphalt, brick, concrete, okay? And we have these units, BTU inch divided by feet square, hour, Fahrenheit, or we have BTU divided by feet, hour, Fahrenheit. What's the difference? Here we have inches in the numerator, feet square in the denominator. Here we don't have inches and we have feet, not feet square here. Okay, so those are two kinds of imperial units that we are going to use for the thermal conductivity. Why do we need both? We're going to do that with Revit too. Today we're not using Revit, but we can do this in Revit. And in Revit, we have these units. But in other tools, we have these units. Okay, so the tool that we are using now in this temperature distribution uses these units, BTU inch, hour, feet square, Fahrenheit. Okay, so if we are working with this tool, we have to use these units, these blue values here. Okay, so I'm going to do it. In this temperature distribution, well, if this is a wall, the thermal resistance, this value, it's always going to be the same. It's 0.625. This is 0.625. Okay, so this is always the same. It doesn't matter the materials that we have here. The indoor value is fixed and the outdoor value is fixed. Okay, so this is going to be 0.625. This is going to be 0.34. Okay, so this is the first one. We don't have to change it. This is thought, well, we only have to change the white cells. The gray ones, we don't have to change them, okay, because they are calculated automatically. So we don't have to change those values. So I'm going to delete this and let's work with this example. So the first material is plywood. Plywood. The thermal conductivity, according to this, well, I can look at the plywood here. We have to find
You passed it.
do we have plywood? Yes, we do have plywood. Okay. It's a 0.75. Well, we can have different sources. In this case, is 0.8 and this is 0.75. If the difference is in the in the second decimal, it doesn't affect. Okay. So we can either use 0.8 or 0.75. Let's use 0.8. Then what's the width? The width is 1. And then this thermal resistance, we know that is width divided by the thermal conductivity. Okay, so in this case, we have the width divided by thermal conductivity. So you don't have to do anything here. The second material is, I think it was fiberboard. Fiberboard. Thermal conductivity is 0.28. And the width is 5 inches. Okay. And then the third material is brick. The thermal conductivity is 5. And the width is 4. Okay. We don't have any materials here. So if you don't have any materials, just type 0 in the width. And the R value is the same. It's 21.07, 21.07. Okay. So that's quite easy. But if we look at the graphic here, we can see the temperature distribution of the wall. But first, before doing this, we have to change something here. You see that the indoor temperature is 70. The outdoor temperature by default is 2. So we have to type 20 here. There you go. So now the temperature is different. It's 70 inside, 20 outdoors. The thermal resistance is 21.7. The thermal resistance is here, it's 0.65, 0.625, 1.25, 17.8. Here it's 18. Well, probably I rounded up here for this exercise. And for the brick, this is 1. Okay, but this should be 5. Okay, so this is 0.8 and this is 0.8. And now it's not 21, it's 20.87. Okay, so probably I rounded it up, but it doesn't matter. Okay, so if the difference is a second decimal, it's not relevant. And here we have the temperatures. So if we hover the mouse here, I see that the temperature here is 68.5. The temperature here is 65.5. Temperature here is 22.73. And temperature here is 20.81. And here is 20. Okay. So by doing this, we should have the same values as we had here. So this is 68.5, 65.5, 22.7, and on the here we have 22.7. This is 20.81, 20.81, and this is 20. Okay. So with this tool, I think it's quite easy to work with this. The only thing is that when be careful, because if you type 0 in this one, we have an error, because here we are dividing 0 divided by 0, which is something that it's not consistent. Okay, so if you don't have materials, type 0 in the width and keep here whatever. Here you can keep any number. Just to prevent the error. And we have errors here, but so far it doesn't affect. If we want just the temperature profile, this is all we need. Okay, so remember that first you have to fix indoor and outdoor temperature here. Second, you have to type the materials. Here you have to type the widths, and here we have the thermal conductivities. If I give you the thermal conductivities, you can type it, or if you don't have the thermal conductivities and you want the thermal conductivity of the brick, here there would be brick somewhere. And brick, we have brick common, we have brick dense, and this is 3.4 and this is 9.25. In this case, brick is, the thermal conductivity is 5. That's because not all the bricks in terms of thermal conductivity are the same. So we can have different kind of bricks here, but it's not that important. Okay, so what really matters is that when we have a thermal insulating material, which is the, for example, polyurethane foam, this is 0.1. If we have polystyrene, it's 0.1. If we have mineral wool, it's 0.2. Okay, thermal insulating materials are around 0.1, 0.2, and then solid materials that we use for construction, it's 10, 9, 5. Okay, but what really matters, this is the fiber insulating board, it's 0.27, and this is the fiber board. Here we have 0.28. Okay, so this is 0.277, so I rounded up, and this is 0.28. But what really matters is the difference between the insulating material, it's 0.1, 0.2, and the solid material that can be 2, 3, 5. So what really makes the difference is this material. And when we have this steep slope, this is the insulating material. Okay, so here the temperature before the fiberboard it's 65, and after the fiberboard is 22. So this is 65 and this is 22. Okay, so the steep slope happens when we have the thermal insulating material. Okay, so I want you to do this on your own, and that's why I have opened this classwork. Well, I didn't do it. Okay, you have here this Excel file. Okay, this ARCH360 dew point vent. I will keep changing this file because I'm still developing it. but you can download this version today. And I want you to complete by next class this quiz. It's a basic quiz about basic concepts in terms of building science. So I want to know if you remember what you learned in 260. It's not graded, okay? So it doesn't affect the final grade, but I want you to open this and I want you to complete this quiz to see if you remember basic concepts of building science. And then you have to complete this classwork. So for this classwork, if you download this one, here we have 3 walls: sandstone 1 inch, air 2 inches, brickwork 4 inches, glass wool insulation 5 inches, and plywood. And here we have exterior and interior. Okay, so you have 3 different walls. So I want you to use this website or this tool, and at the end, if you are done with this, I want you to copy. If we download this one. Okay, if this is wall 1, I want you to copy and paste this table here. Okay, you can type here wall 1. And copy and paste all this, but I want to see the materials. Well, you have to type the right materials here. And I want to see the thermal resistance, the total thermal resistance, and I want to see this graphic with the temperatures here. Okay. So this is what you have to do. You have to open this PowerPoint. You have to open this Excel file, and you have to type the thickness, and you have to search for the thermal conductivity on this table, and then use this, and then copy and paste.